Hi everyone, welcome to another Becoming a Doctor tutorial. We're glad you've joined us. So today it will be on Embryology 1 by Marianne. So just some house rules of how it's going to work. Any questions and comments, feel free to put them in the chat. If you have any questions in a more general sense, not about the presentation, that can wait to the end, we recommend you put it in the Q&A. And also for this lecture, there will be some short answer questions. So for those, we advise when Marianne asks it, you private message it to her and then she can look for the answers. But otherwise, have fun and I will pass it over to Marianne.
Hello everyone, welcome to this session on embryology. My name is Marianne. I'm a fourth year medical student at Imperial College London. So this year I'm intercalating in reproductive and developmental sciences. So it's a BSc where we do a lot about embryology and all about the different reproduction pathways. So I hope you'll find this tutorial useful, and let me know, yes, if you have any questions, please, as was said, do post in the chat, and we can get started. Just a little disclaimer. This content is just for education purposes. So the lecture outline for today, first of all, we'll look at the events and cell biology of development. So the different, factors that are involved and all the different cell processes. Then we will look at fertilization and what happens there. And finally, we will look at systematic embryology for the first, 3 to 4 weeks or so. So including pre-implantation development, then implantation, and then finally, gastrulation and neurulation, which are funny words, but we'll soon know what they are. Don't worry. So first of all, let's start by the cell biology of development. So there are 4 simple processes in all cells of the body, which are proliferation, movement or chemotaxis, differentiation, which means, changing from the usual cell that you were into a different cell, and loss or apoptosis. So actually in mature somatic cells, they only show one characteristic at one time. However, in an embryo, the cells may show three of the first characteristics simultaneously, which is really different to mature somatic cells. So the means can proliferate, move, and differentiate at the same time. Yes. So how is this process regulated? Using hormones and growth factors. Hormones can act in different ways. They can act in an autocrine manner, which is the cell that is producing hormones or growth factors, in fact, and acting on itself. So this is autocrine. Paracrine is when a cell is acting on its neighbor, so a cell that is nearby. We all know endocrine regulation of hormones, right? But this is happening in the blood, and it's not possible in the embryo at this stage because the embryo doesn't have a vascular system at all. We're talking of a few cells, So hormones and growth factors are very important in the embryo, and they act in an autocrine and a paracrine manner. So there are also changes in receptor expression. So it means that there are different level of hormones, but also different level of receptors on the cell. So there can be more receptors, which is upregulation, or less receptors, which is downregulation. And how these hormones work, they work by a gradient and a combination of gradients. So it means that the cells can act on the neighbors, and they can be spatial and temporal regulation. This means that this gradient will change in time and will also change in space. So this is just about how cells work and communicate with each other. So I hope this all makes sense. Are there any questions so far? Okay, so I think we can move on to fertilization and different events and processes. So again, let me know as we go along if you have any questions at all. So fertilization is day 0. Of course, it's so after the oocyte is released from the ovary, over here. Sorry, where's my mouse gone? So after the oocyte is released from the ovary, it is picked up by the fallopian tube, which you can see, and fertilization usually takes place in the fallopian tube. So if you guys would like to tell me your thoughts, where in the fallopian tube does fertilization usually take place? So there's a poll going on right now, so make sure you vote. Is it, as you can see on the diagram, fimbria, infundibulum, ampulla, or isthmus? If you're not sure, don't worry, this is all about, learning, and I'm going to tell you the right answers as we go. Just a few more people would like to vote. Okay, great. So I'm going to share the results. Actually, yeah, the right answer is the ampulla, correct. So the ampulla, as you can see, is the large part of the fallopian tube, essentially. It has a lot of space. The fimbria is the part that is going to pick up the oocyte when it's released. Sorry, let me close this poll. Perfect. So, sorry, as I was saying, the fimbria will pick up the oocyte as it is released from the ovary, and then it will travel through the infundibulum, ampulla, and usually if fertilization is going to occur, it occurs and then the fertilized zygote is going to travel down to the uterus, but we're going to talk more about that later. So well done for you guys got the right answers. Let's keep this up. So what happens during fertilization? So there are lots of sperms trying to get in the oocytes, and the head of the sperm is going to undergo a reaction, which is called the acrosomal reaction, which I'm going to talk more about in the next slide, so don't worry. And so you can see over here that it's a sperm like crowding around the oocyte. And when the acrosomal reaction occurs, some chemicals are released, and they help the sperm make its way through the zona pellucida, which is this area around the oocyte. Once one sperm has connected with the plasma membrane of the oocyte, there's a cortical reaction, which is happening just inside the oocyte, and there's huge release of cortical granules, and it means that no other sperm cells can enter the oocyte. It's very important because if you get 2 sperm cells, then you're going to have too much genetic material and a huge problem, of course. So then once the sperm cell, the head of the sperm cell enters the oocyte, and the 2 nuclei will dissolve and the chromosomes will mix. This is very important because some textbooks say that the nuclei fuse. They don't actually fuse. The membrane dissolves and then it rebuilds itself eventually, right? When the new material is created. So they don't fuse, they dissolve. And this will create a full set of genetic material, right? Half a set from the mom, half a set from the dad, and it creates a new full set of material, which we call diploid, that is completely unique. So in this slide, I just have a little reminder of diploid and haploid, if that can help with anyone. Haploid is half the genetic material, so they only have 1 copy of each chromosome, and diploid means they have 2 copies of each chromosome. I can see I have a question. The question is, how does the release of cortical granules prevent other sperm from entering? That's a quite complex, advanced biology question, but the chemicals send messages to the plasma membrane, which is usually quite permeable in the case of the oocyte, and suddenly there's a reaction in the membrane, that closes off the zona pellucida and the plasma membrane around the oocyte. It's quite complex, advanced biology, but the cortical granules act on the zona pellucida and the plasma membrane. I hope that answered your question. So yes, what is the genetic material inside the sperm cell? It's haploid, so it has half a set of genetic material. As we can look at the sperm cell here. Here's the nucleus in the head, and the acrosome, which is just at the top of the head. So we can see how the sperm cell is going to use its head to burrow its way into the oocyte, and when the acrosome is going to be opened, is going to help the sperm cell move through the zona pellucida. So I'm going to move on to looking more at the oocyte, which is a bit more complex than the sperm cell. Oops. So the oocyte, as you can see, there's a nucleus, a nucleolus, and then, so there's the plasma membrane that we're talking about, and the zona pellucida, which is a complex coat of protein and glycoprotein that act as a sort of protection, but also can have the cortical reaction later. And around the zona pellucida, there's the corona radiata, and that is made of cells from the follicle, because the oocyte is released from a follicle in the ovary, and there's lots of follicular cells around the oocyte. So corona is other cells. I have another question. I'm just going to check right now. The difference between the nucleus and the nucleolus, that is a good question. It's not very important for the sake of this lecture. It's about how the DNA is compacted differently. I think the nucleolus is more compacted, and it's basically all the nucleus is DNA, right? And the nucleolus is some special type of DNA that does something special. I'm not too sure, and it's in all cells of the body, right? It's not specific to the oocyte. Sorry, the sperm cell, the cells in your skin, the cells in your gut, they all have a nucleus, and inside the nucleus, they have a nucleolus. It'd be interesting to look it up for later, what the role of the nucleolus is. But it's not important in this lecture. Sorry, I couldn't answer your question more. So importantly, the oocyte is halted in meiosis in metaphase 2. So it means that it still has its it still has full genetic material. It hasn't completed its meiosis yet. And it only has one polar body. We're going to talk more about polar bodies in the next slide. So once it is fertilized, it will resume meiosis and generate a second polar body. And at the end, it has the exact same amount of DNA like the sperm cell, a haploid set of genetic material. So to further illustrate what I was saying, sorry, this picture is coming out a little blurry. So meiosis is in two parts, meiosis 1 and meiosis 2. And so in meiosis 1, one polar body is generated with the polar body is essentially the genetic material that the egg does not need. So it's halving its DNA each time, and whatever it doesn't need, it casts it on the side, right? So at the beginning, it has a pair, as you can see, sorry. It has a pair, 2n = 4. It has a pair of double chromosomes. Then it halves, it has a pair of single chromosomes. And then at the end, it will only have one single chromosome at the end of meiosis. So I'm just going to check, I think, another question. No, okay. And so the polar body is all the genetic material that it does not need. So it's, like I said, you can see here, the 2 is halving and then halving again. Every time you take away something that you don't need, you put it in a polar body. That's essentially what happens. So a good way to check if fertilization has worked is seeing, has the second polar body appeared? Because if there is a second polar body, you can be sure that the sperm cell made it inside and fertilization has worked, because otherwise there wouldn't be a second polar body. That's very important. Anyone have any questions on this? Because this polar body story can be a bit confusing. Yeah, as you can see here, the nucleus of the nucleus of the oocyte and the nucleus of the sperm cell are going to, disintegrate and make a new nucleus. And now the oocyte and the sperm have met, and they make a zygote now. So we're going to move on to see how the zygote develops. So this is systematic embryology. We're going to see the different events and processes. So yes, this is the general timeline. So fertilization on day 0, pre-implantation development from day 0 to day 6, implantation on around about day 6, and then gastrulation and neurulation. So let's keep this timeline in mind as we travel through what happens in the development of the zygote. So a quick review, the conceptus is everything that is resulting from the fertilized egg. So this means the fetus, of course, but also, as we can see in this, this photo at the bottom, the membranes around the fetus, the umbilical cord, the placenta, these are all resulting from the fertilized egg, right? They're not, the membranes and the placenta is not from the mother. It's all cells that are from the zygote. So this is what we call the conceptus. So embryology, this is supposed to be embryo. The baby is the baby before it's clearly human. So 8 weeks post-fertilization. Again, that should say embryo, not embryology. So I put 8 weeks PF and then 10 weeks GA. PF is post-fertilization because that's how we time it in embryology. However, in the clinical world, you know, if you're seeing a patient, you're not going to know the exact day of when fertilization happened. So we time in gestational age, and gestational age is the time from the last period that the woman had. And so as we know that a woman has a period and then 2 weeks later she will ovulate, usually, this is why gestational age is 2 weeks after the fertilization age. I hope that makes sense. So it's 8 weeks PF and 10 weeks GA. That's a very important, whenever you look at an embryology diagram, make sure you know, is it post-fertilization or is it gestational age? Because otherwise you'll get confused by 2 weeks, and 2 weeks is a long time in embryology, you know. So embryo is before 8 weeks, it's before the baby looks clearly human, and the fetus is the baby for the rest of the pregnancy. So as you can see on the 2 diagrams, on the first image, it does not look clearly human. In fact, it could develop into a mouse or a cat or any sort of mammal, we don't know. And then after this 8 weeks, it finally looks like a tiny human that's developing. Any questions at all? I'm just going to wait a few seconds if you guys have any questions. Okay, so let's start then with pre-implantation development. I'm going to shorten it to PID later. So it's from day 0 to day 6. In terms of where the zygote is, as we said, it was fertilized around the ampulla. It's traveling down slowly, down the isthmus, down the interstitium, and into the uterus. So it will arrive in the uterus and settle on day 6. In the meantime, as it's traveling down, it's dividing, okay? So it's dividing, very importantly, by cleavage divisions. So that means, as you can see, that the big cell, the big oocyte, is just dividing into 2, and then into 4, and then into 8. It means that it's not becoming any bigger. So it means that the 2 cells have half the amount of cytoplasm as the 1 cell before, and again and again. So the 8 cells have the same amount of cytoplasm as the first cell at the beginning. So this is why we call it cleavage. It's like cutting through. It's not actually creating new cytoplasm, okay? And it has the same size and the same shape as before. Does that make sense? Then on day 4, we start calling it a morula. A morula means a little mulberry in Latin. I don't know if it looks like a mulberry or raspberry, whatever. But so it's undergoing compaction and differentiation. So compaction is making something more compact. So it means that the cells that were just randomly scattered around this little ball of 8 cells suddenly get together and then differentiate. So the cells at the center are slightly different from the cells that are on the outside. So this is what MORULA looks like under the microscope. So you can see around here, there's still this layer of the zona pellucida, and the cells that are stacked on top of each other still have the exact same size as the initial zygote at the beginning. That was one cell. So that reminds us how big the oocyte is. You know, it's as big as 8 cells almost. As you can see on this, again, microscope view, that they're getting compacted. And they're getting differentiated as well on day 4. Okay, so on day 5, they changed to a blastocyst, day 5 to 6. So a blastocyst is when there's a formation of a cavity, right? So it's a fluid fill cavity, and it's called the blastocyst cavity, or there are different names for it. And it shows the first big differentiation in cells. We can see the inner cell mass, which is at the center, this big bulk of cells. And then we can see the trophectoderm, which is a lining of cells around the outside. So the inner cell mass is going to become the future embryo. And the trophectoderm is going to become the future placenta. I just wrote that for simplifying, but also all the membranes, etc., etc. Okay. So yes, this is very important. This is the whole conceptus, right? So the trophectoderm is still part of the conceptus, even though it will not be part of the embryo. It will become the placenta. Any questions at all on the blastocyst or the MORULA? Yes, I can see a question. PID, I just said it is a pre-implantation development. Sorry, it was just to make things a bit shorter, otherwise the slide would be crowded. So on this slide, pre-implantation development, PID. Okay. If there's no questions, we can move on to some little interactive questions to see if you guys have been understanding this okay. So I'm going to launch the question. Okay, so the first question, what is the first step of pre-implantation development? Right, so I'm going to share results. Yeah, that's correct. It's cleavage division. So division is not clear enough, that's why it's wrong. Asymmetric division is wrong because we know it's symmetrical, it's exactly half and half. And multiplication is also wrong. So good job, most of you got this one. If not, don't worry. Now, moving on to the next question. So next question, what is the second step of pre-implantation development? Sorry, the questions in the poll, they don't match the ones on the slides. So if you want to post in the chat A, B, C, or D, and then it will be easier. So the 4 options are neurulation, MORULA, blastula, or blastocyst. I can see lots of chat. Yes, yes, so that's correct. It's B, MORULA. Thank you for being reactive and posting in the chat. Great. So the second step is the MORULA that is compacted and differentiated. So question 4. I will launch question 4. After the MORULA stage, the conceptus develops a cavity and becomes... Good job. I think that's quite a straightforward question. There's just a little trick somewhere in the question. So yes, the correct answer was the blastocyst. So another word for blastocyst is blastula. So if that was blastocyst, blastula, that's the same thing. But interestingly, blastomere is something very different. A blastomere is the name of the cell that makes up the blastocyst, if that makes sense. So that was quite a trick from my part, but just to make sure. So blastocyst and blastula are the same thing, but blastomere is different. A blastomere is a cell that makes up the blastocyst. Okay. So a little summary of pre-implantation development: fertilized egg, cleavage, morula, then blastocyst. Great. Any questions so far? Please feel free to message. Have some water. So there's a question that says, what does the cavity in the blastocyst become? We're going to see that later on. Don't worry. There are a few cavities that develop, and then we're going to see what happens to them. So thank you for that question. If you don't mind waiting, we're going to see that very soon. Okay. So we're going to move on to up. Yes, finally, implantation. So before the fertilized zygote is going to implant the blastocyst, in fact, it needs to hatch from the zona pellucida, because the zona pellucida, as we said, is quite a dense structure of protein around the oocyte and then around the zygote. But then it needs to come out of that, not only to grow in size, finally, but also so it can implant. The zona pellucida is very useful because it protects the zygote all the way as it's going down the uterus. It's a very tough layer, and so if the blastocyst was just going out without protection, it might be harmed along the way. But so once it's come into the uterus and it's ready to implant, the blastocyst will hatch from the zona pellucida. This is called hatching. And the blastocyst will implant in the uterine lining, so aka endometrium, but more specifically primed endometrium, but we also call it the decidua. So there's a difference between endometrium and primed endometrium. So we can cover that in another lecture on reproduction, but the endometrium needs to be ready to welcome the blastocyst by secreting certain factors and having the right blood flow and glands that are working. And so the endometrium will only be like primed for 2 or 3 days in a cycle. And so it means that up to 10 days that can work, but after, the window is very short. Afterwards, the endometrium won't be ready anymore. So it won't be able to implant. Okay, so at this point in the blastocyst, let's look exactly at what's happening there. The inner cell mass has differentiated again into a bilayer disc. How exciting. So as you can see in this diagram, there's the epiblast and the hypoblast, okay? So again, there's a second small cavity here. The epiblast is this big layer on top and the hypoblast is on the bottom. And the bilayer disc will give rise to all the tissues, okay? And that's as the blastocyst is implanting. You can see over here this big sort of pink wave is the trophectoderm starting to invade the decidua. So if we zoom a little bit, we can see this cell is the trophectoderm that are still looking like cells, And this is a trophectoderm that look like, you know, an invasive wave. And here inside is the, you know, the inner cell mass has become the epiblast and the hypoblast. Okay, yeah, bigger zoom, that's what I thought. This is the cells that look like an invasive wave. They're called syncytiotrophoblasts, and the cytotrophoblasts are the ones that remain looking like cells. The syncytiotrophoblasts, they fuse and they become a big invasive wave of trophoblasts. I've got a question. No, I don't have a question at the moment. So there's two cavities around here, right? The blastocyst cavity and the amniotic cavity. So we're going to see later what happens to these two cavities, okay? Any questions at all? I just put this diagram of the orange here to remind you that we're seeing this as a slice, but actually it's a ball, right? So the embryo is not thin and flat. It's actually, of course, a ball that is going to implant in a like 3D, remember the 3D aspect, okay? So we have the bilaminar disc made of the epiblast and the hypoblast. If you want to message in the chat, but message me privately the answer to this short question. Message me privately so the other people can't see the answer. Name 2 places where implantation occurring could cause harm to the mother, if you guys know this. Yeah, so ampulla, isthmus, infundibulum, cervix. So yes, thank you for all your suggestions. So essentially it's, in a few simple terms, something that's not the endometrium in the uterus, right? So if it implants in the fallopian tube, that can cause a lot of harm to the mother. In the intraperitoneal space, in the ovary, and the cervix, we refer to this as an ectopic pregnancy. And why can it cause harm and fertility? It's because it is not made to welcome a fetus, right? The uterus is made to welcome a fetus and expand, but it will cause a lot of bleeding suddenly if a fetus implants in the fallopian tube, right? Because it is not the right place. So the tube can burst and bleed, and there could be an internal hemorrhage that can be fatal to the mother. That was just for everyone's clinical interest. Okay, sorry, but it's also an important question that got asked in exam in 2009 at Tutor. So let's remember, we have our bilaminar disc made of epiblast and hypoblast, right? And this bilaminar disc is going to form into a trilaminar disc made of mesoderm, endoderm, and ectoderm. So this is called gastrulation, right? Okay, so this is a complicated word we need to learn, gastrulation and mesoderm, endoderm, and ectoderm. We're going to see step by step how these we're going to see step by step how it's going to how it's going to form from 2 layers to three layers. Okay, so this occurs around 14 to 18 days post-fertilization. So gastrulation, first step, as you can see over here, this is very important. So it all starts at the primitive node, okay? The primitive node, which is just over here, and it moves along cranially to caudally. So it means it moves from the head, from where the head will be to where the bottom will be, right? And it moves down as all the epiblast cells in the center decide they want to create a new layer between the epiblast and the hypoblast, okay? Sorry, not all the cells. The cells in the primitive node decide that they want to create a new layer. So they're like, okay, I'm going to create a new layer. And they proliferate, which means they divide, and they differentiate into mesoderm cells. And they move into the space between the epiblast and the hypoblast, okay? And this, they go down the primitive streak. Remember the 3D structure? They move down the primitive streak, moving between the two layers as they go. Okay, this can be quite confusing. So, but don't worry, we're going through step by step. So we've seen mesoderm, they come from the epiblast, right? Then the mesoderm cells are going to move one step further. They're going to start replacing the hypoblast cells. So the hypoblast cells move off. Not all of them die. Some of them are kept. We're going to see a bit later in the yolk sac. But most of the hypoblast cells are all replaced and they undergo apoptosis. And the mesoderm cells replace all the hypoblast cells apart from a few over here. I hope this all makes sense. So mesoderm comes from the epiblast, and then the endoderm also comes from the epiblast because it comes from the mesoderm, right? So we can see the movement of the cells replacing the hypoblast over here. And then finally, the epiblast that is still there will differentiate into ectoderm, okay? So this means that we have our 3 layers: mesoderm, endoderm, ectoderm. So I hope this all makes sense. Let me know if you have any questions. So one thing that I want to mention that is very important while you guys type your questions, this happens under the control of the notochord. The notochord is underneath the, do you remember at the beginning, the primitive node? So like, why do the cells suddenly decide they want to move inwards? Is because there is a signal from underneath saying, actually, you are going to become the primitive node and you are going to differentiate now. And so this, underneath the primitive node will always remain this notochordal process, or we call it, okay, underneath the primitive streak. Where does the endoderm come from? The endoderm comes from all the cells that have invaded and become the mesoderm. Some decide to go a bit further, right? And then invade the hypoblast, and they replace the hypoblast. So again, the hypoblast doesn't become the endoderm. That's quite important, okay? So it's a good question. The endoderm comes from the epiblast that differentiates into mesoderm and then differentiates into endoderm again as a second step. So this was gastrulation, right? And why is it so important? Is because it gives rise to to all the tissues in the body. So every time you read an embryology textbook, it's going to mention endoderm, mesoderm, and ectoderm. So don't forget about them. They come up all the time. So the endoderm will give the gut, the liver, and the lungs. The mesoderm will give the essentially lots of things in the middle: the skeleton, the muscles, the kidneys, the heart, the blood. And the ectoderm will give the skin and the nervous system. Okay, so as you can see on this diagram here, it's color-coded, right? You can see the endoderm has the most surface. Is that correct? And then the ectoderm is all around and also makes a tube in the center. We're going to see how this tube is created, right? And the mesoderm is everything else. Okay, so someone asked what becomes of the cavities. You can see the cavities are still there. There's a little cavity here and a little cavity here. They're just part of the mesoderm now. And the cavities will eventually be filled in. Okay, so we're going to have, I think, oh yes, a short answer question. So please, if you want to type me a message, if you can try to do a private message so that only I can see your answer. And tell me what are the 2 cell types before gastrulation and 3 cell types after gastrulation? So it'll be like quick fire questions. 2 cells before, 3 cells after. Yeah, I see a lot of good answers. Perfect, great. So the 2 cells before, that's quick recap, epiblast, hyperblast, and then mesoderm, endoderm, ectoderm. Perfect. So now quite more tricky questions. If you can go to the poll. Oh, there we go. So question 5, the endoderm. Sorry, is the poll working? Up, there we go. I just launched the poll. Okay, so the endoderm, does it come from the hyperblast? Does it give the lung and stomach? Does it give the digestive system? Okay, so, oh, a few more people want to vote. Okay, so I'm going to end the poll. So the correct answer is the lungs and the stomach, okay? So I see most of you have answered the digestive system and blood vessels. Actually, the blood vessels come from the mesoderm, right? So that's not correct. Indeed, the endoderm gives rise to the digestive system, but the blood vessels come from the mesoderm. So that was a very tricky question, sorry. And the kidneys come from the mesoderm as well. So actually the correct answer is the lungs and stomach, okay? But when I say stomach, also it includes it's not only the stomach, it's also the rest of the digestive system that comes from the endoderm, okay? And it doesn't come from the hyperblast, it comes from the epiblast. Okay, so we're going to move to the next question. The ectoderm. If you guys want to vote. Yes, so most of you have given the right answer for now. Keep these answers coming, guys. Yeah, keep voting. Great. So most people answered correctly. Sorry, there was a little trick here because, of course, central nervous system is correct, but it's not the best answer because it's missing the skin, right? And the ectoderm gives rise to the central nervous system, which is the brain and the spinal cord, but also the skin. Okay. And so the second option gives the spinal cord and vertebrae. The vertebrae are bones, right? So they come from the mesoderm. So the spinal cord is indeed from the ectoderm, but the vertebra, that's not correct. Vertebrae are bones and they come from the mesoderm. And again, it doesn't come from the hyperblast, it comes from the epiblast. No one answered that, so good job, everyone. Again, if you have any questions, keep asking in the chat or keep answering, keep asking as you want. So moving on to the next question. I mentioned this briefly, but oops, sorry. Oh, sorry. This question is for later. I forgot. We're going to talk, about neurulation now. So do you remember, as I said, that underneath the primitive node and underneath the primitive streak, right, sorry. Underneath the primitive node and underneath the primitive streak, as I'm pointing, right, there's a group of cells called the notochord, and that are actually, you know, sort of influencing cells above them to give them instructions, right? So these are going to influence the cells of the ectoderm to transform, okay? So this is called neurulation. It's the differentiation of the ectoderm to become the central nervous system, okay? So when does it happen? Before gastrulation is complete, so up to 2 weeks, but it means that gastrulation is still going on towards the bottom end of the embryo, when actually neurulation has started at the top end of the embryo. So top end is cranial and bottom end is caudal, okay? And so how does it happen? Again, under the control of the notochord, which is in the mesoderm between the 2 lateral plates, okay? So you can see the ectoderm, and you can see actually it used to be a trilaminar disc, right? Now it's beginning to curve a little bit and is going to fold over onto itself, right? We're going to see this later. But as it's changing from 2 layers to 3 layers, it's at the same time creating this neural tube that we're going to look at now. So the definition of neurulation is the neural, the ectoderm layer transforms into a tube. That's what we're going to at the end, isn't it? Okay, so please look carefully. This is quite tricky. The ectoderm, just above the notochord, it forms into a thickened area called the neural plate, right? And then it's going to fold slowly. That's the second step. At day 20, it's going to fold into what we call the neural folds. And the mesoderm underneath is thickening to support this folding, right? At the same time, it's beginning to slightly curve around laterally, right? So the end of the embryo is this way, the head is this way, and the bottom is this way. So these are the 2 sides, right and left. So on the right and the left, the ectoderm is starting to make a fold, and then is going to increase in size and make a tube. Okay, so different steps: neural plate, 1, neural fold, 2, and neural groove, 3. And they finally fuse to form the neural tube. Can you see what stage we've arrived to at the end? We have a tube that is independently closed off, and on top of it, we have the rest of the ectoderm that is going to form the skin. That is amazing because it means we created a tube inside of another layer of ectoderm on top. And as you can see, the tube is, the whole embryo is folding laterally now. So this is like folding in all directions, isn't it? It's folding laterally. So it means the ectoderm is eventually going to go all the way around to create the skin all around your body. Any questions at this stage? Because it can get a bit confusing, neurulation. So this is how the tube forms, and if we're looking at it from an other view, right? So because there are more complex structures at the cranial end, this will take more time, right? That's why it starts first, and it's going to take a bit more time. But so it's completed in different stages. It goes down slowly and slowly and slowly, closing off from the cranial towards the caudal end, okay? And then it creates the anterior neuropore and the posterior neuropore, and eventually everything is going to fuse and form the different structures. So this neural tube is going to form the spinal cord, right? And at the top is going to actually form the brain. This whole very complex part is going to form the whole brain of the individuals. That's why the neural tube is so vital. And that's why the ectoderm cells are so incredible in that they can form the brain structure. And also they can form another structure that is the skin. It's totally different. Okay, so any questions right now? Please ask away in the chat if you have any questions. Okay, if you don't have any questions, I hope this is a bit clearer now that we've tried to see it in, from different steps and different views as well, to try to imagine what's going on in a 3D aspect. Okay, so what happens if there is a failure of neurulation? That means if the tube doesn't close properly, right? So this is called spina bifida. I think some of you might have heard it before. So you can see in this baby, unfortunately, the neural tube hasn't closed properly, right? So there can be different levels of problem. If it doesn't close a bit, then it's just missing a bone, because the bone from the mesoderm is not going to form if the neural tube isn't completely sealed off, right? So this is spina bifida, sort of like level 1. It's called occulta. It means it doesn't cause any problems. However, if the certain layer of spinal cord is actually popping out, like protruding, the meninges are protruding. It's called meningoceal. And if the whole spinal cord is protruding, that can be a very bad problem. So for the fetus, which can lead to complete or partial paralysis, bowel bladder dysfunction, clubfoot, back pain, spasticity. How do we prevent this failure of the neural tube closing? Because it's just a neural tube that forgot to close in one little space, right? The prevention is folic acid, but this needs to be given before conception, because as we know, neurulation is happening around, day 20, okay? So day 20, the woman doesn't even know she's pregnant yet. She has just maybe missed the period by 1 or 2 days. She doesn't know what's going on. So if the woman starts taking folic acid when she's pregnant, that is too late, right? So we advise all women, when they're trying to conceive, to take folic acid supplement to prevent this spina bifida. Another failure of neurulation is anencephaly. So this is very, very unfortunately when the neural tube doesn't close but towards the head of the embryo, right? And this means that the brain will not form. So anencephaly in Greek literally means lacking the brain, right? So unfortunately, this is not a viable condition, and the baby will die within either before it's born or within a week of being born. Okay, so this is when the neural tube does not close. There's a question, how does folic acid help the tube close? Well, very good question. It doesn't, but it helps the cells multiply correctly. And so, because the reasons the tube isn't closing is because this process is so fast and maybe the cells don't have time to develop. So the cells are multiplying, and then if they don't multiply fast enough, the tube will stay open a tiny bit. So if you give folic acid, the cells are able to multiply faster. This is quite complex. This is due to folic acid being a key building block of DNA. So the cells can't replicate if they can't replicate their DNA. So making sure they have lots of folic acid means they can replicate their DNA, and means they can have lots more cells whenever needed to close the tube. Does that make sense? I hope that answered your question. Very good question. Okay, so a quick poll. This will be the last poll. The notochord, which I spoke of briefly, is it part of the ectoderm? Is it part of the mesoderm? Does it control the development of the mesoderm, or does it control the development of the endoderm? I'm going to wait for a few more answers. So we're running a little bit short on time, so I'm just going to end the polling and share results. So actually the correct answer was it's part of the mesoderm, right? And it's underneath the ectoderm, is going to control the ectoderm, is going to send signals, paracrine, like we said at the beginning. It's communicating with other cells around it and saying, now you ectoderm have to become a neural plate, okay? And then it's giving instructions, now you have to become a neural fold, and then neural tube, etc. So the notochord is part of the mesoderm, and it's controlling the development of the ectoderm. Okay, I think I have a question. Okay, no, that's all good. Okay, so this is just wrapping up what's going to happen afterwards. So there's going to be folding of the embryo, right? We have seen how the embryo is folding laterally, okay? But now it's going to start folding in the anterior posterior direction as well. So this is why I put this little image of human in the fetal position, because it's showing how it's going to fold head first and legs first as well, right? So this is the cranial part, and this is a caudal part, right? And it's folding onto itself, okay? And then it starts folding laterally. So this is a step we've already talked about, but I just want to make it very clear. When the neural tube is forming, the ectoderm is growing onto the side like arms. The reason I put this CT scan here is to show you that this is a lateral view, right? So if you're right now in front of your screen, right? Imagine stretch out your arms to the side and create a big hug, right? This is lateral folding, okay? And then your arms meet in the middle and they fuse in the central midline, okay? So again, if you're in front of your computer, just mimic the lateral folding of the embryo. And then you can mimic the anterior posterior folding of the embryo, okay? So the neural tube is closing, the ectoderm and everything is also folding laterally. And as you can see, is going to form a little 3D ball, which is containing two tubes, right? We can see it is containing the neural tube that we really explained a lot, the neural tube, but also, sorry, I can't find my mouse every time. Okay, great. And it's also containing this new tube that was created by the lateral folding, okay? Can you see here is the endoderm. It's fusing here and it's going to create its own separate tube in yellow. I'm sorry, the photos come out a bit blurry again. So at first, right, the endoderm is all flat and is going to, as everything is folding around it, is going to create a little pouch and then it's going to be closed off and become an actual tube, okay? And then around everything else is the mesoderm, okay? So I hope this makes sense about what happens next in the embryo. And hopefully you can have another lecture for the rest of the embryo development after 3 to 4 weeks, what happens next. So just a little reminder of the general timeline that we talked about: fertilization, pre-implantation development from day 0 to 6 with the morula and then the blastocyst, okay, for the blastocyst cavity. Then implantation into the endometrial lining on day 6 or around day 6. Then gastrulation, that goes from a bilayer disc to a trilayer disc, right? And then neurulation, which is the ectoderm that is folding into a neural tube. Okay, so this was a summary take-home messages. Try to remember these keywords, and I hope you understand all of these processes better now. Do you have any questions at all? And I'd like to, if you guys want more information, I invite you to check out my Instagram at Marianne Does Medicine, where I give lots of information about fetal anomalies and more about embryonic development if you're interested. And while I can answer some questions, please fill in the feedback form. It only takes less than a minute. And I'm going to start answering some of the questions now if there's more questions popping up. The question is, what does the endoderm create other than the gut? So the endoderm, right, is going to form a tube that crosses the whole embryo near the neural tube, right, and is going to become the whole gut, and also is going to become the lungs. That's very important, right? So imagine this tube is going to fold itself, right, like this, to become the stomach, the intestine. It's also going to become the liver. It's also going to become the lungs, right? So that's what the endoderm creates. I'm trying to see if I forgot anything. No, that's it. So the gut is quite straightforward because it's one whole tube, right, going from the mouth to the anus. But also remember that it also forms the lungs. That's very important. And the liver, the pancreas, everything like that. If you have any other questions, I'm happy to answer them. There was a question that says, how can the fetus implant in the ovary? How would it move to there? So it is more likely in women that have pre-existing conditions, and that means that the fallopian tubes may have a wheel tape, or they may have some adhesions blocking the way. So you know how the zygote is traveling down to the uterus. If it can't really get through, it might just stay there and implant in the tube, or it might try to go the other way to see, actually, maybe I got it all wrong, and maybe the uterus is the other way around. So the zygote might try to go back, and then it might accidentally implant either in the ovary or in the abdominal cavity. Okay, that is more likely, again, if a woman has some pre-existing condition. So where does the endoderm come from? It comes from the epiblast that is slowly invading between the epiblast and the hypoblast. And then this epiblast is going to replace the hypoblast and become the endoderm. Okay. I've answered this question. Okay, so I think I've answered all the questions. I hope you guys enjoyed this tutorial, and make sure you fill in the feedback form. So if everything is good on your side, I'm happy to end the tutorial. Thank you so much for you guys for tuning in.